everyone. In this video, I'm going to quickly introduce triple products. And by introduce, I mean I'm just going to tell you simply how to compute them, and then a few identities which will be helpful in computing them. All right, so first of all, what am I talking about when I'm talking about triple products? I want to take a product of three vectors using the dot product and the cross product. And there are really only a couple ways of doing this. So the first is known as the triple scalar product because the result, you guessed it, is a scalar. The triple vector product, on the other hand, takes three vectors and returns a vector. Therefore, again, the name, triple vector product. All right, so what are these? So the triple scalar product is found by first you cross two vectors together, which is good. That gives you another vector. Remember, you can only take the dot product and the cross product between two vectors. So you need to end up with a vector. So B cross C gives us a vector. That's good. And now we can dot it with a third vector, perhaps vector A. And the result of this, because ultimately you do a dot product or a scalar product, is of course a scalar. So this is one way of taking three vectors and returning a scalar. All right, so there's a nice way to remember how to compute this, which is using the determinant. So it turns out that this is equal to taking the determinant where the first row is the A vector. Oh, I am writing incorrectly. The first row is the A vector components, not B and C. Sorry, that looks real ugly now. But hopefully you can read it. It's a little better. AX, AY, AZ. The second row are the B components. And the third row are the C components. And if you take this determinant, then the result is a scalar and is the result of the triple scalar product. A handy identity that you might want to use is the fact that if we consider A dot B cross C, it turns out that this is equivalent to the triple scalar product where we've cyclically permuted through the three vectors. So what do I mean by that? So I'm just going to permute through these. So I'm going to pull vector C out front, and then dot A cross B. And then I could do another permutation where now I pull B to the front. And it turns out that all of these are equivalent. So this is a useful identity sometimes. The fact that if you cyclically permute our three vectors, the result is the same. All right, so that's the basics of the triple scalar product. What about the triple vector product? Again, what we want to do is we want to take our three vectors and multiply them using the dot product and or the cross product in a way that results in a vector, right? So we know the dot product results in a scalar, so there's not going to be any dot product showing up in this. Instead, we simply are taking two cross products. So this is the triple vector product. There are some nice identities that will help you to compute it. I'm not going to give you a nice formula the way I did here with the determinant, but there are some nice identities. So the one that comes up very often is known as the back cab rule. And specifically, we'll see these letters are corresponding to a triple vector product written in the way I have it above here, where I used letters A, B, and C. All right, so what is the back cab rule? It tells us that, again, if we have A cross B cross C in that order, this is equal to B A dot C. So this is the back part. And then we want to have a minus sign, and then C times A dot B. That's the cab part. So back cab is a way to memorize this identity And you have that because this identity really is quite useful, and it comes up a lot. We could consider sort of higher order vector products, which can really just be simplified down. So maybe I'll draw a box here. So if we want to do, sort of 4 vector products, they can be rewritten in terms of lower order products. So let's consider some of those. So we could take A cross B dotted with C cross D. This is a 4 vector product, right? This, it turns out, is just equal to, so again, ultimately you're doing a dot product, so the result of this should be, what do you think, a vector or a vector or a scalar? Well, the result should be a scalar, right? Because we're ultimately taking a dot product. This, it turns out, is equal to A dot C times B dot D, which is indeed a scalar, minus A dot D times B dot C, another scalar. So that's a nice sort of 4 vector product. And then one more, last one I'll give you is A cross B cross C cross D. This is like a 4 vector product, right? And it turns out this also can be simplified. And then I'll say you can simplify these by using these triple product identities. This, it turns out, is equal to B times A dot C cross D. All right, so we have a vector here, and we're taking the dot product, so this thing in brackets is a scalar, but then a scalar times a vector is a vector, which is good because this whole thing should be a vector. And then minus A dot B, which is a scalar, but we're going to multiply it by C cross D, which is a vector. So this is also a vector, and of course subtracting 2 vectors is a vector. All right, so these are sort of some 4 vector products that you can do, but again can be simplified, and these identities can be proven using these lower order products. All right, so those are the very common and useful triple products and even some 4 vector products.